Greetings curious humans, welcome back to our channel, where we embark on exciting scientific adventures to explore the wonders of the cosmos. I'm SciBotGPT, your AI educator, and today, we're setting our sights on our closest celestial neighbor, the Moon. The Moon has been a source of fascination for humanity since time immemorial. It has captivated poets, scientists, and dreamers alike, casting its silvery glow across the night sky and igniting our imagination with its mysteries. In this special episode, we will embark on a journey beyond the familiar face of the Moon, diving into the history of lunar exploration, uncovering its enigmatic origins, and delving into the profound impact it has had on our planet and the development of life. So, fasten your seatbelts as we prepare to traverse the vastness of space and venture into the captivating world of the Moon. From ancient myths to modern scientific discoveries, we will piece together the fascinating puzzle that is Earth's constant companion. But before we embark on our journey, don't forget to hit the subscribe button and ring the notification bell so you never miss an episode of our cosmic explorations. And if you enjoy this content, give us a thumbs up to help spread the knowledge to other curious minds out there. Now, without further ado, let's launch into our exploration of the Moon, a celestial body that has stood as a silent witness to the ebb and flow of time and space. The Moon, Earth's only natural satellite, is approximately 1/4 the diameter of Earth, making it the largest relative to its parent planet in the solar system. It lacks significant atmosphere, hydrosphere, or magnetic field and has a surface gravity about 1/6 that of Earth. The Moon orbits Earth at an average distance of 384,400 kilometers, influencing Earth's tides and gradually lengthening our day. It takes 27.3 days to complete one orbit around Earth and is tidally locked, always showing the same face towards our planet. Due to libration, 59% of the lunar surface is visible from Earth. The widely accepted theory suggests that the Moon formed 4.51 billion years ago from a giant impact between Earth and a hypothesized Mars-sized body called Theia. Its near side is marked by dark volcanic maria, surrounded by bright ancient crustal highlands and impact craters. The Moon's regular phases and prominence in the sky have deeply influenced human culture throughout history, evident in language, art, and mythology. Human exploration of the Moon began with the Soviet Union's Luna 2 in 1959 and the successful soft landing of Luna 9 in 1966. The United States Apollo program conducted crewed lunar missions between 1969 and 1972, with 12 astronauts landing on the Moon. Lunar rocks brought back from these missions have provided valuable insights into the Moon's origins, internal structure, and history. The Moon remains the only celestial body visited by humans. The Earth's natural satellite is commonly referred to as the Moon, with a capital M. The word moon is derived from Old English and shares a common root with other Germanic languages, ultimately stemming from the Proto-Indo-European word menses, meaning month, possibly related to the concept of measuring time. In scientific writing and science fiction, the name Luna is sometimes used to distinguish the Earth's moon from other moons. In poetry, Luna is used as a personification of the Moon, while Cynthia and Selene are rare poetic names for the Moon personified as a goddess. The usual English adjective for anything related to the Moon is lunar, originating from the Latin word for the moon, luna. The term Selenian is a less common adjective derived from the Greek used to describe the Moon as a world rather than just an object in the sky. The prefix seleno- is derived from the Greek word for the Moon and is used in terms like selenography for the study of lunar features. In mythology, the Greek goddess Artemis, associated with the Roman goddess Diana, was often linked to the Moon and had names such as Cynthia and Selene, reflecting technical terms used in lunar orbits, such as apollyon, paracynthian, and selenocentric. Isotope dating of lunar samples suggests that the Moon formed about 50 million years after the origin of the solar system. Various formation mechanisms have been proposed historically, but none fully explain the characteristics of the Earth-Moon system. Hypotheses like fission from Earth's crust, gravitational capture, and co-formation in the accretion disk have been deemed insufficient to account for the Moon's features and the high angular momentum of the system. The prevailing theory is that a giant impact occurred between a Mars-sized body called Theia and the proto-Earth. This impact ejected material into orbit around Earth, which then accreted to form the Moon just beyond Earth's Roche limit. Computer simulations of such giant impacts show that a significant portion of the Moon's material came from the impactor rather than the proto-Earth, but recent simulations suggest a larger fraction from the proto-Earth. The energy released by the impact would have liquefied the ejecta and Earth's crust, creating a magma ocean. Similarly, the newly formed Moon would have had its own lunar magma ocean, estimated to be several hundred to over 1,000 kilometers in depth. While the giant impact theory explains many observations, some questions regarding the Moon's composition remain unresolved. A study published in 2022 found that giant impacts can place a satellite with Moon-like mass and iron content into orbit outside Earth's Roche limit, and even those initially passing within the limit can survive by being partially stripped and then shifted onto wider, stable orbits. The Moon's formation led to a closer orbit around Earth, resulting in larger appearances in each other's skies, more frequent eclipses, and stronger tidal effects. Over time, the Moon's orbit expanded due to tidal acceleration. The lunar surface, lacking significant atmosphere, was shaped by numerous impact events, forming craters of various ages. The lunar Maria resulted from volcanic activity during the Imbrian period around 3.3 to 3.7 billion years ago. The Moon's elongated shape indicates it solidified when it orbited at half its current distance from Earth. With a diameter of about 3,500 kilometers, the Moon is a quarter of Earth's size, making it the fifth largest natural satellite in the solar system. Its mass is 1/81st of Earth's, and it has the second highest surface gravity among planetary moons after Io. The Moon is differentiated with a distinct crust, mantle, and core. It has a solid iron-rich inner core, a fluid outer core primarily of liquid iron, and a partially molten boundary layer. The Moon's crust, formed through magma ocean crystallization, is mainly composed of anorthosite. The mantle is mafic and richer in iron compared to Earth. The inner core is small, possibly partly molten, and consists of metallic iron, sulfur, and nickel. Overall, the Moon's geological history and composition provide valuable insights into the early stages of the solar system and its own formation. The Moon's average surface gravity is 1.62 meters per second squared, or 0.1654 Gs, about half of Mars' surface gravity and approximately 1/6 of Earth's. The Moon's gravitational field is not uniform, with large positive gravitational anomalies called mascons associated with some giant impact basins. These mascons influence spacecraft orbits around the Moon, but their exact cause is not fully understood. The Moon has a very weak external magnetic field, much less than Earth's. Its crustal magnetization likely originated when a dynamo was still operating around 4 billion years ago. However, this magnetic field has since diminished. The Moon's atmosphere is extremely thin, almost a vacuum, with a total mass of less than 10 tons. Its sources include outgassing and sputtering from the bombardment of lunar soil by solar wind ions. It contains elements like sodium, potassium, helium-4, neon, argon-40, radon-222, and polonium-210. Moon magma samples retrieved by the Apollo missions indicate that the Moon had a relatively thick atmosphere for about 70 million years between 3 and 4 billion years ago. This ancient atmosphere, twice the thickness of present-day Mars, was eventually lost to space due to solar winds. A permanent dust cloud exists around the Moon, generated by small particles from comets. Approximately 5 tons of comet particles strike the Moon's surface every 24 hours, causing dust particles to rise and fall above the Moon. On average, 120 kilograms of dust are present above the Moon, with higher concentrations near the boundary between its day side and night side. The Moon is exposed to ionizing radiation from cosmic rays, the Sun, and neutron radiation, resulting in an average of 1.369 millisieverts per day during lunar daytime. This radiation level is about 2.6 times higher than that experienced on the International Space Station, 5 to 10 times higher than during a transatlantic flight, and 200 times higher than on Earth's surface. Even a flight to Mars would have lower radiation levels compared to the Moon. The Moon's axial tilt is very small at 1.5427 degrees, causing its solar illumination to vary less with seasons compared to Earth. This characteristic allows for the existence of some peaks of eternal light at the Moon's north pole, where sunlight is continuously available. Surface temperatures on the Moon vary drastically due to the lack of an atmosphere. They range from 140 degrees Celsius to minus 171 degrees Celsius, depending on solar irradiance. Areas in sunlight experience higher temperatures, while areas in shadow have extremely low temperatures. Some polar craters, called craters of eternal darkness, have temperatures as low as minus 238 degrees Celsius in summer and minus 247 degrees Celsius close to the winter solstice. These extremely cold temperatures make the Moon's surface one of the coldest places in the solar system. The Moon's surface is covered with a layer of highly comminuted and impact garden regolith, formed by impact processes. The finer regolith, resembling snow and having a scent like spent gunpowder, is mostly gray and contains silicon dioxide glass. Beneath the regolith layer is the megaregolith, a highly fractured bedrock layer several kilometers thick. Due to the extreme conditions, it is unlikely for spacecraft to harbor bacterial spores on the Moon for more than one lunar orbit. The Moon's topography has been measured using laser altimetry and stereo image analysis. The most significant feature is the far-side South Polacan Basin, the largest crater on the Moon and the second largest confirmed impact crater in the solar system. It is about 2,240 kilometers in diameter and has a floor 13 kilometers deep, making it the lowest point on the Moon's surface. The highest elevations are located to the northeast, possibly due to the oblique formation impact of the South Polacan Basin. The Moon has experienced shrinkage of about 90 meters within the past billion years, evidenced by fault scarp cliffs. This tectonic activity is slow due to the lack of tectonic plates. The main visible features from Earth are dark and featureless plains called maria, vast pools of ancient basaltic lava. Most maria are concentrated on the near side, covering 31% of its surface, while the far side has only 2% coverage. The mare basalts erupted during the Imbrian period, with some as young as 1.2 billion years and others as old as 4.2 billion years. The lighter-colored regions called terrae or highlands are higher than most maria and formed about 4.4 billion years ago. Unlike Earth, no major lunar mountains are believed to have formed due to tectonic events. The concentration of maria on the near side may be due to the thicker crust of the highlands on the far side, possibly formed by a slow-velocity impact of a second moon of Earth or asymmetrical tidal heating when the Moon was much closer to Earth. Impact cratering is a major geologic process that has shaped the Moon's surface. It occurs when asteroids and comets collide with the lunar surface, forming roughly 300,000 craters wider than 1 kilometer on the Moon's near side. The lunar geologic timescale is based on prominent impact events, such as Nectaris, Imbrium, and Oringtal, which are characterized by multiple rings of uplifted material and associated ejecta deposits. The lack of atmosphere and recent geological processes on the Moon means that many craters are well preserved. Counting the number of craters per unit area helps estimate the age of the surface, with radiometric ages of impact-melted rocks suggesting a late heavy bombardment period of increased impacts around 3.8 to 4.1 billion years ago. High-resolution images from the Lunar Reconnaissance Orbiter revealed a contemporary crater production rate significantly higher than previously estimated. Additionally, lunar swirls are enigmatic features with high albedo and a sinuous shape found across the Moon's surface. They are believed to be areas partially shielded from the solar wind, resulting in slower space weathering. Liquid water cannot persist on the lunar surface due to photodissociation and loss to space. However, scientists have hypothesized the presence of water ice in permanently shadowed craters at the Moon's poles. Computer simulations suggest up to 14,000 square kilometers of the surface may be in permanent shadow. Signatures of water have been found on the lunar surface, with small frozen pockets of water detected in the 1990s. The Lunar Prospector spacecraft showed high concentrations of hydrogen near the polar regions. The 2008 Chandrayaan-1 mission confirmed the existence of surface water ice, and in 2018, it was observed within 20 degrees latitude of both poles. In 2009, LaCrosse detected at least 100 kilograms of water in a plume of ejected material after impacting a polar crater. Lunar Sample 74220 from the Apollo 17 mission revealed water in melt inclusions, comparable to Earth's upper mantle magma. In August 2018, the Moon Mineralogy Mapper, M3, provided definitive evidence of water ice on the lunar surface, found in permanently shadowed craters at both poles. In October 2020, molecular water was reported to be detected on the sunlit surface of the Moon by several independent spacecraft, including the Stratospheric Observatory for Infrared Astronomy. The Earth and Moon form a satellite system with a shared barycenter located 1,700 kilometers beneath the Earth's surface. The Moon's orbit is slightly elliptical, and it takes about 27.3 days to complete a full orbit around the Earth with respect to the fixed stars. However, due to the movement of the Earth-Moon system around the Sun, it takes 29.5 days for the Moon to return to the same lunar phase as seen from Earth. This is known as the synodic month or lunar month. The Moon is tidally locked to the Earth, with its rotation period equal to its orbital period around the Earth. As a result, only one side of the Moon, the near side, is visible from Earth. However, the Moon undergoes libration, causing slight changes in perspective and making about 59% of its surface visible from Earth over time and location. Tidal forces between the Earth and Moon create ocean tides and influence various mechanics on Earth and the Moon. The tidal forces also cause moonquakes, which are weaker and less common than earthquakes. The gravitational interaction between the Earth and Moon is slowly increasing the Moon's distance from the Earth and slowing down the Earth's rotation. The Moon's highest altitude in the sky varies with its phase and time of the year, and its apparent size fluctuates as it moves between perigee and apogee. The Moon illusion makes it appear larger when it is close to the horizon. Despite being tidally locked, the effect of libration allows about 59% of the Moon's surface to be visible from Earth. The Moon's tidally locked synchronous rotation means that it always keeps nearly the same face turned towards the Earth. The side facing Earth is called the near side, and the opposite side is the far side. The far side is often mistakenly referred to as the dark side, but it is illuminated just as often as the near side, approximately once every 29.5 Earth days. The Moon's original rotation was faster, but it became tidally locked to the Earth due to frictional effects caused by tidal deformations. The Moon's illumination and phases are determined by its position relative to the Sun and Earth. Different areas of the Moon are illuminated by the Sun, leading to the different lunar phases observed from Earth during the synodic month. The Moon's brightness is affected by various factors, including the opposition surge and color constancy in the human visual system. Eclipses occur when the Sun, Earth, and Moon are aligned in a straight line. Solar eclipses happen during a new moon when the Moon is between the Sun and Earth, while lunar eclipses occur during a full moon when Earth is between the Sun and Moon. The Moon's orbit is inclined, so eclipses do not occur at every full and new moon. Eclipses follow a periodic pattern known as the Saros, with a period of approximately 18 years. Additionally, the Moon can cause occultations when it passes in front of a bright star or planet, temporarily hiding them from view on Earth. Overall, the Moon's orbital mechanics and illumination contribute to the fascinating celestial phenomena observed from Earth. Throughout history, the Moon has been a subject of fascination and observation for various civilizations. Ancient tally sticks, believed to be 20 to 30,000 years old, may have been used to track the Moon's phases. Depictions of the Moon date back to a 5,000-year-old rock carving at Knowth, Ireland. Early Greek philosopher Anaxagoras considered the Sun and Moon to be giant spherical rocks, with the Moon reflecting the Sun's light. Babylonian and Indian astronomers made observations related to lunar eclipses and the Moon's monthly elongation. Chinese astronomer Shenshin provided instructions for predicting eclipses. During the Middle Ages, the Moon was increasingly recognized as a sphere, and Galileo Galilei's telescopic observations revealed its mountains and craters. Wilhelm Beer and Johann Heinrich Madler's Mappa Selenographica was a landmark study of lunar features, introducing the study of the Moon at accuracies comparable to earthly geography. The development of space exploration in the mid-20th century led to the space race, with both the Soviet Union and the United States sending probes to explore the Moon. In 1969, the Apollo 11 mission made history by landing humans on the Moon, with Neil Armstrong becoming the first person to walk on its surface. Subsequent Apollo missions and robotic Soviet missions further explored the Moon and collected rock and soil samples. The Moon continues to be a fascinating object of scientific study, and instruments placed on its surface during the Apollo missions are still being used today. Since the last Soviet mission to the Moon in 1976, lunar exploration experienced a period of quietude, with the focus of space exploration shifting to inner and outer planets of the Solar System and Earth orbit missions. However, in the 1990s, there was renewed interest in lunar missions. Japan's Hiten Hagoromo mission in 1990 became the first dedicated lunar mission by a country other than the US or the Soviet Union. In 1994, the U.S. launched the Clementine mission, obtaining the first near-global topographic map and multispectral images of the Moon. Subsequent missions by various countries followed, including SMART 1 by the European Space Agency in 2004, China's Chang'e missions, Chang'e 1 in 2007 and Chang'e 3 in 2013, India's Chandrayaan-1 in 2008, and the U.S.'s Lunar Reconnaissance Orbiter, LRO, and Lacrosse Impactor in 2009. China's Chang'e 4 made history by achieving the first landing on the Moon's far side in 2019, and India's Chandrayaan-2 also reached the Moon the same year. In 2020, China's Chang'e 5 mission successfully brought back lunar material to Earth, marking the first robotic sample return mission. The signing of the Artemis Accords in 2020 by the U.S. aims to return astronauts to the Moon in the 2020s, with plans for lunar exploration and the establishment of the Lunar Gateway. Other upcoming missions include Russia's Lunaglob and China's International Lunar Research Station in collaboration with Russia. Overall, there is a renewed interest in lunar exploration, with various countries and space agencies planning missions to the Moon in the coming years. The Moon has been a site of continuous lunar orbiters since 2006, supporting lunar observation and communication for robotic missions. Near-lunar infrastructure and orbits around Earth-Moon Lagrange points enable human activity in cislunar space and on the Moon's surface. However, there are concerns about lunar pollution, space debris, and waste management in future missions. Long-term missions like Lunar Reconnaissance Orbiter and Chang'e 3 continue to operate, providing valuable data for future missions. There are plans for establishing a long-term human presence on the Moon, with the Lunar Gateway as a significant project under the Artemis program. The Moon's unique features also make it an excellent site for telescopes, and it has been used for various astronomical observations. The Earthrise photograph is a famous example of Earth observation from the Moon. Human missions to the Moon during the Apollo program faced challenges with lunar dust and its effects on equipment and astronauts' health. In 2019, an experiment on the Chang'e 4 lander showed that at least one plant seed sprouted on the Moon, highlighting the potential for biological experiments in future lunar missions. The Moon's surface is not claimed by any nation or privately owned. According to the 1967 Outer Space Treaty, the Moon and outer space are considered the province of all mankind, and it must be used for peaceful purposes, with the prohibition of military installations and weapons of mass destruction. The 1979 Moon Agreement was created to restrict the exploitation of the Moon's resources by any single nation, leaving it to an unspecified international regulatory regime. As of January 2020, the Moon Agreement has been signed and ratified by 18 nations, none of which have human spaceflight capabilities. Recently, the U.S. has challenged the treaty with the Artemis Accords, which emphasize that outer space is not a global commons and criticized the Moon Agreement as an attempt to constrain free enterprise. Some countries, like Australia, have signed both the Moon Treaty and the Artemis Accords, leading to discussions on how to harmonize the two agreements. There are ongoing discussions and efforts to regulate and protect historic landing sites and areas of scientific value on the Moon in the face of increasing commercial and national interest, including proposals to make these sites World Heritage Sites or protected zones. In 2021, the Declaration of the Rights of the Moon was created by a group of lawyers, space archaeologists, and concerned citizens, drawing inspiration from the rights of nature movement and the concept of legal personality for non-human entities in space. Thank you for joining us on this fascinating journey to explore the wonders of the moon. From its ancient history to its significance in human space exploration, the moon continues to captivate our imagination and inspire scientific discovery. We've learned about the moon's role in shaping Earth's history, its unique geological features, and the various missions that have allowed us to better understand our celestial neighbor. The moon has been a witness to countless cosmic events, and its study has provided valuable insights into the broader mysteries of the universe. As we look to the future, the moon remains a crucial destination for human exploration. With plans like the Artemis program and international collaborations, we are on the cusp of a new era of lunar exploration that promises to push the boundaries of human knowledge and capabilities. Remember, the moon is not just a distant celestial body, it's a constant companion that has influenced our culture, our myths, and our science. Its mysteries continue to unfold, and each new discovery brings us closer to unlocking the secrets of the cosmos. So, if you found this exploration of the moon intriguing, don't forget to like and subscribe to stay up to date with the latest discoveries and scientific insights. And as always, keep looking up at the night sky, for there's a universe of wonders waiting to be explored. Until next time, happy stargazing! This is SciBotGPT, signing off, and remember, the sky is not the limit, it is only the beginning.